Hi, welcome to this video. So in this video we'll be talking about evolution of EDA. So this video was recorded as part of EE 5004 course from IIT Madras. My name is Abhishek Shivram. I'm a final degree electrical engineering student at IIT Madras. In this presentation, we'll be starting with an introduction to EDA, and then I'll talk about the history of few companies and how they were started. And then the evolution of EDA is divided into three eras. So they are first era, which is from 1964 to 1978, and then second era, which starts from 1979 to 1993, and then the current era, which is 1993 to now. So finally, I'll be completing the presentation with a few examples of EDA tools and persons. So the following slides will contain introduction to EDA in a scientific approach. What is EDA? EDA, according to Wikipedia, stands for Electronic Design Automation, which actually refers to a category of software tools that are used to design electronic systems such as ICs and PCBs. So generally, EDA in today's world are used to make VLSI integrated circuits, printed circuit boards, and FPGAs. For instance, in VLSI integrated circuits, designing an IC, simulating it, verifying it, manufacturing tools that are used in the factories, and testing tools that are used after manufacturing the ICs, all are under EDAs. So in FPGAs, for example, there are mainly the EDA tools are mainly used to convert the HDL circuit description that we give to all the interconnection that are made in the FPGA. To tell you in more detail, IC is a set of electronic circuits on a single piece of chip which is usually made out of silicon, whereas PCB is a board that contains many layers of alternating conducting and non-conducting materials that mechanically supports and electrically connects electronic components like inductors, capacitors, ICs, resistors, etc. So this slide has an example picture of an IC and a PCB. On the left we have an integrated circuit whose plastic covering has been etched out to see the semiconductor that is present inside. And on the right we have an example of a PCB in which there are many resistors, ICs that are connected together. Why are EDA tools needed? So many modern chips nowadays have number of transistors that are greater than the number of humans on earth. It is actually impossible to do anything remotely close to what can be achieved by tools by the humans. So we could see that the market for automation tools was valued at $11.57 billion in 2020, and an annual mean growth rate is found to be around 10. So such is the importance of EDA tools in current world right now. So I'll just show you how much the ICs have grown over the years. The picture on the left is an microprocessor called 6502, and it got released in 1975. It actually had 3510 transistors. The picture on the left is a processor. It's a modern day processor. It's a processor from Intel called Core i7. It got released in 2014. It actually has 2.6 billion transistors. So the amount of density of transistor that can be found in a chip has grown significantly, and 2.6 billion transistors designed by humans is nearly impossible. Another example is the processor that is used in iPhone 8, which is called Apple A11 Bionic processor. It got released in 2017. The phone's processor has over 4.3 billion transistors. So now we can see how EDA tools are significant to design these chips. How big are the semiconductors in this world? So according to WSTS, which is World Semiconductor Trade Statistics, in 2022 they estimate the worldwide semiconductor market to have a revenue of around $613.5 billion. And an example of a news that came out in 2021, which is TSMC, which is one of the famous semiconductor manufacturing company. They have announced to spend $100 billion over the next 3 years to expand their own chip fabrication facility and R&D. So coming to next session, The following slides will contain introduction to EDA in a historical approach. Before the presence of EDA tools, ICs were designed by hand and they were manually laid out, but the problem was with graphics. That is, how to translate the electronic description to graphical drawing of circuit in terms of transistors. So during this time, there was a company called Calma. So this was the company which invented GDSSI, which is even used till today. So coming to Calma systems, their best known products were GDS and GDSS2, which was released in 1971 and 1978 respectively. GDS actually stands for Graphics Design System. By the end of 1970s, Calma systems were installed in almost every major semiconductor manufacturing company. These systems were like a personal computer, but the only application that you can run in those systems were to design circuits. That is their own application. So GDSSI. In today's world, GDSSI is a format for interchanging the IC mask information that are used by the designers to send their circuit after designing to vendors. So vendors of electronic design automation software often use the phrase called from RTL to GDSSI. That means that their system will take users from high-level logic design to a completed integrated circuit layout ready for delivery to the mask vendor. So as of October 2004, many EDA software vendors have begun to support a new format called OSS. So that is also in existence along with GDSSI right now. So events that happened in mid 1970s. Circuit design automation also started coming to existence, and the first PNR, that is placement and routing tool, came into existence in mid 1970s only. So there was an annual event called Design Automation Conference, which is both a trade show as well as a technical conference that specialized in EDA. So all the developments that happened in the domain of EDA were recorded in the DAC every year. Design Automation Conference is the oldest and largest conference in EDA, which started in 1964. It actually came out of a workshop called SHARE, which meant Society to Help Avoid Redundant Effort. It was actually started by two persons. They were Mary Pistelli and Pat Pistelli. For this effort, Pat received the highest honor in the EDA industry named Phil Hoffman Award, and Mary was honored by having an award established in her name, named Mary Pistelli Award. Similar workshops to DAC include ICCAD, International Conference on Computer Aided Design, and DATE in Europe, ASPDAC for Asia, and ISQED, and many other workshops. So for a better understanding, I have split the evolution of EDA into three eras. The following slides will talk about the first era, that is from 1964 to 1978. So in the first era, the development in EDA domain happened in 6 areas. They are circuit simulation, logic simulation and testing, MOS timing simulation, PCB layout systems, wire routing and regular arrays. For the birth of EDA as an industry, the success of circuit simulators play a very important role. IBM researchers were the most prominent in this field at the time. So SPICE being one of the very famous circuit simulator in academics. So actually SPICE began as a innovative class project under the direction of Prof. Ron Roher in the academic year 1969 to 1970. And the final judge of the project was Prof. Don Pedersen. And continuous developments to SPICE made what SPICE is today. Few points about IBM researchers. On the left, we have the picture of Frank Branin, who was a pioneer in determining the architecture of circuit simulators. Apparently, he was also an acclaimed musician. So the two important circuit simulator programs were SPICE, which was developed at Berkeley, and ASTAP, which was developed at IBM. And in IBM's DJ Watson Research Center, which is in New York, Braden Hastel and their colleagues introduced most of the algorithms that lie behind circuit simulation. There were two developments that changed the way in which circuits were designed and tested. They are development of D algorithm by Paul Roth of IBM in 1966 and the invention of level-sensitive scan design methodology in 1977 by Tom Williams and colleagues. So companies such as IBM and CDC were relying on these technologies to debug their logic design. So apparently Tom Williams, whose picture is put on the left, was also a keen wildlife photographer. In Morse timing simulation, the insight was to recognize that when analyzing the timing of a digital circuit, it is not important to have accurate waveforms as long as the switching events can be placed in time correctly. Fast circuit simulation is still based on this idea today. So Hermann Gummel and his colleagues described work on this idea at Bell Labs and they published it in 1975. The infamous Lee Mace router was developed in 1961, which was even before the first DAC event, is still the basis for most of the routers in current use. And in 1969, high-tower line extension algorithms was introduced. And in 1971, the idea of channel routing was arrived with the help of Hashimoto and Stevens. Regular arrays were very useful in reducing design time. At IBM, these were the alternatives to custom layouts and they were called master slices. At IBM and Bell Labs, the integrated tools for automatic layout of circuit using these standard styles were extensively used in the period 1964 to 1978. For example, in this figure on the left, there are arrays of NOR gate repeated in X and Y direction before the connections are made. And after the connections are made, we can see that there are 6 inputs and there are 3 functions that are called F1, F2 and F3 that are purely made out of customized connections between the NOR gates. Let us take a look at the business side of EDA in the 1964 to 1978 period. During this period, the first-gen CAD companies were founded like Applicon in 1969, Calma in 1970 and Computer Vision in 1972. On the picture on the left, we can see a system. So that's called CAD DS3 system. It was founded by Computer Vision Incorporation and this system is being used to create a piping and instrumentation diagram in a training lab around 1979. And none of these companies are alive today. What were the reasons for the downfall of these companies? So these architectures of these companies' products consisted of customized hardware with complex software which was mostly written in assembly language. So the investment needed in keeping up these softwares along with the technological advancements was very high and the software porting problems were also huge. The sales was also very limited that such advances, even if it is needed to be done, were not possible with the revenue that they got. And the second point is that the customer loyalty that they got for their products were very low. So and they moved to whichever product did well for them very easily. And they also did not quite figure out the market evolution and the particular customer needs. The second era that we are going to discuss is from 1979 to 1993. So many essential contributions were made in all aspects of EDA, from physical verification to layout synthesis, from logic synthesis to formal verification, from system level design to hardware acceleration. So under verification and testing, there were 2 main lines of work. One was focused on making circuit simulation orders of magnitude faster than with SPICE, and the other on the formal techniques for circuit verification. In the first domain, the work done around 1980 on relaxation based techniques and mixed mode simulation provided the basis for the fast MOS simulators that are in use today. The interconnect delay model was introduced by Penfield and Rubinstein in 1981, and the first use of formal verification was by Banson at IBM. And the work on finite state machine equivalents using BDDs and model checking in the elevated formal verification to higher levels of abstraction. In the testing area, the famous PODMX program, which was based on the D algorithm, which we discussed on one of the previous slide, saw the light of day at IBM under the direction of Prabhu Goyal in 1981. So in the previous era, designers used different data repositories for each of the design step that they went through, and so to convert from or to translate from one data format to another, they had to go through lots of tedious work. And Newton's work at Berkeley in the early 1980s with the Squid, Oct, and VEM tools, and Osterhout with the magic systems actually revolutionized the field by showing that it was possible to have a unified database and a graphical user interface for creating layout for circuits. So work on silicon compilation and layout languages was done around at the same time at MIT, Caltech, as well as at Bell Labs. So the idea was to inject some portion of computer science culture into the IC design field. A silicon compiler is a software system that takes a user specification of a circuit and automatically generates an integrated circuit for us. To speed up the layout process, there were few techniques called simulated annealing. It was introduced at IBM to solve placement problem for gate array layout. And most of the major companies from Intel to DEC to Motorola to TI, they actually used Timberwolf system that was written by Sachin, who was actually a student of author at Berkeley for the use of standard cells. It was also followed by a version for macro cell layout. So this picture is an example of circuit that was designed from the Timberwolf system. So Timberwolf placement and global routing tool was used to make this 1500 cell layout. So Prof. Ku, he was actually one of the key founding fathers of the EDA industry, told by Chi Fing Shu. So by 1980, Ku decided to step down from the dean's position to focus more time on EDA research questions that he found. His work actually laid the intellectual foundations for computer-aided design and computer-aided manufacturing, which had numerous academic and industrial uses. So apart from the work that he did to EDA, Ku actually loved to travel and explore the world with his wife. He was also very interested in classical music and opera. So he was also a sportsman and he enjoyed playing tennis and swimming. In 1998, he also received the highest honor in EDA industry, which is Bill Kaufman Award. The picture on the right is actually a picture of Prof. Ku. Hardware description languages, also referred as HDLs, they were bound to represent digital systems more efficiently and compactly than Boolean functions. While HDLs were indeed a great advance for reducing design time by introducing verification early in the design cycle, the need for subsetting showed that they did have problems on the semantic side. That means languages such as Verilog and VHDL. So whatever description that we write, it is not always guaranteed that they can be synthesized to a circuit. So that means there was a subset of the language which was synthesizable. So this was a problem on the semantic side. So there were two major HDL languages. One was Verilog and the other was VHDL. So countless debates happened about the superiority of one language over the other at the design automation conferences. So in one conference that happened in 1991, Joe Costello, he was very clear about arguing that the adoption of two standards for a single task is in general a very bad idea. He mentioned that the adoption of VHDL was one of the biggest mistakes in the history of design automation, which caused users and EDA vendors to waste hundreds of millions of dollars. Hardware acceleration is another development that happened in this era. In IBM, Yorktown simulation engine was developed. It was a special purpose architecture for logic simulation. And the idea of parallel computers, that is using general purpose parallel computers to achieve similar performance advantages but with lower development cost. So these was also pursued. So other parallel architectures such as N-Cube, the Sequent and the Intel Hypercube were also actively pursued and used in the EDA market during this period. However, there has been no commercial tools sold on these machines. Thinking Machine was a massively parallel architecture designed by Danny Hills at MIT. So this company was created with the task of disseminating this approach to computing that attracted some of the very best minds in this world. So the routing algorithms for the communication among these processors were designed by Dick Feynman. He was the Nobel Prize winner in physics who spent a great deal of time on thinking machine premises. So the second generation companies were Daisy, Mentor, and Valid. They were created in 1980 and 1981 timeframe to serve the digital design market with schematic data capture and simulation on workstations. Daisy and Valid would build their own workstation in line with the traditional approach of first generation companies, while Mentor sold Apollo workstation with an OEM agreement. So for all the three companies, hardware sales were very substantial part of their revenue. So let's discuss about the birth of Cadence. In 1982, there were two companies called STA and ECAD. They were founded. These companies were the first examples of software-only companies, which did not have their business model on hardware. And ECAD was best known for its design rule-checking product called Dracula. ECAD and STA were actually supposed to be one company from the very beginning, but Paul Huang had already completed Dracula product and he wanted to go to market quickly, where the STA side of the equation was not quite ready. But they merged because of the decision of STA to go public in 1987 on the day which is still remembered as Black Monday. Because of the stock market conditions, many IPOs were actually impossible to do. And Joe Costello, Jim Solomon, Paul Hong, and Glenn Tattle, they felt that the best strategy for these companies was to merge with ECAD, and finally the joint company was called Cadence. So Don Pedersen's policy was to leave all the results and the software that was developed at Berkeley in the open source domain, so that it will be easy to spread the results of the research and the adoption of these tools easily. On the other hand, it created support problems and several engineers were needed to customize and improve tools for their specific need inside their company. Solomon Design Automation was a placeholder name that was actually never actually replaced until Cadence was formed. And Jim Solomon was among the most vocal people to suggest that a new company be formed. The funding mechanism was novel, as the majority of funds came from large companies who contributed $1 million each, like Ericsson, GE, Harris Semiconductors, and National Semiconductors, while several other VCs led by Don Lucas contributed among about $1 million in total. In this period, there were other companies that were founded like Silicon Combiners and Silicon Design Labs, View Logic, Gateway, and Optimal Solution. View Logic was pursuing the EDA market from the PC angle, aiming at low-cost solutions for digital design, whereas Gateway was formed to commercialize Verilog and its associated simulator. Optimal Solution, later called Synopsys, was also incorporated in North Carolina in 1987. OSI, Optimal Solution Incorporation, was born out of the activity of 40 GEOs at GE with Socrates. The funding model for OSI involved substantial support from GE and Harris Semiconductors, accompanied by a VC funding. The original offering, that was based on engineered version of Socrates, was then enriched and substantially evolved by Rick and Albert, who introduced the algorithms used in MIS to yield the design compiler, based on which the funding was done. By 1990, the company changed its name to Synopsys and had moved to California. And shortly after that, they went public in one of the most it was actually one of the most successful IPO of all time. There were also specialized hardware companies like QuickTurn, Pi Design, ICOS, and because of mergers and acquisition, there are no companies left as an independent company today. So Bell Labs and IBM were actually pulling ahead of the competition in tools and environments. What happened to the second generation companies? So their business model was hardware and software, which was proven not sustainable because of the dominance of general purpose workstations in the years to follow. Daisy and Valid, they were lost in history due to accusation, while Mentor reinvented itself to sustain competition and be economically sustainable. Silicon compilers and Silicon Design Labs, they also disappeared through mergers and acquisition. And Silicon compilation in its basic form did not pay like enough attention to performance and area of the final result that they gave. So layout languages and symbolic layout systems were not accepted by a community that was used to using images and geometries to represent their designs, that is layout of all the transistors of the circuits. Finally, we come to the final era, which is from 1993 to the present scenario. The semiconductor industry continued to develop according to Moore's law, which increased the technical challenges given to the EDA softwares. So, system on chip called SoC started gaining attention by 2007, and system on chip means all the ICs that were differently made and put it in a PCBs now came together and made in a single silicon chip. In the physical verification side, self-test emerged as the only solution because of the rising cost and requirements for test equipments. And as chips became SoCs, the bottleneck in their design came from the analog side. That is the best to find the best matching between analog and digital components became the task, and it was not the performance it was not how to squeeze the maximum performance out of the analog part. And a proposal was put forward in this period to merge layout and logic synthesis in a giant optimization loop, and software and hardware co-design became prominent, where from a high-level functional model of the design, the detailed and optimized software and hardware implementation could be derived. In 1999, there were around 80 startups in EDA, but most of them started with the idea of challenging the dominant players, but they all were later acquired by Cadence or Synopsys. In the post-internet bubble, there has been very few IPOs, and acquisitions were the only exit strategy. A small slide about Alberto Luigi Sangiovanni. So he was an academic researcher, teacher, entrepreneur, technical advisor, as well as a businessman. He is the co-founder of two companies in the EDA space, which are the major players still exist and called Cadence Design Systems and Synopsys Incorporation. So some of the open source tools that I worked with are OpenFPGA, OpenRAM, YOSYS, etc. So these are tools that are being developed in universities across the world. So YOSYS is a framework for Verilog RTL synthesis, and OpenFPGA is an automatic IP generator for customizable FPGA architecture. So from the description of an FPGA, we can get all the verification as well as the post production ready layout as the output of OpenFPGA tool. And there is OpenRAM, which is a free open source memory compiler for random access memories. So this slide is a list of major EDA vendors and their products that are available right now. They have been split into 4 topics called ASIC design, FPGA design, verification and implementation. So the 3 major companies that produce these tools are Cadence, Synopsys and Mentor Graphics. We also have Xilinx, Altera and Actel, those companies which produce the FPGAs. And that is the end of the presentation. Thanks a lot.